So this is going to be a bit different from what was covered in the class, but nonetheless I think it's relatively useful. So what we're going to be looking at is how Hamiltonian flows vary under nonlinear transformations. So as was mentioned in the course, Hamiltonian flows live within the phase space. I will call it curly M. And a nonlinear transform is just a transformation that takes every set of coordinates in M and turns it into a new set of coordinates. So here the old set is X, and the new set is Y. And just in this circumstance, X is the familiar Q and P. Yeah, very neat, very neat. And then Y is just a new transformation. Now, for this purpose, for this presentation, I need to define very specifically what I mean by a Hamiltonian flow. A Hamiltonian flow is a flow that can be defined via a Hamiltonian operator, H, and the two Hamilton's equations, so dH, and then Q negative equals PI dot, and then dH dPI equals QI dot. Alright. So, what's convenient about defining it in this way is that I can now kind of combine these two equations using this matrix W, which is a antisymmetric matrix. 0, and I believe it is I, negative I, 0. In this circumstance, I is just the unit matrix in whatever dimension we're in. Doesn't really matter. This is generic to any number of dimensions. So using this, I can then rewrite the whole equations of motions, these two guys, into a single equation. X dot I is equal to Wi j, then H comma j. Now, notation-wise, the derivative with respect to the x coordinate j is denoted as comma j. It's just a thing that exists. So in this circumstance, this is equal to Wij d Hamilton dxj. Alright. So that's neat. Yeah, that's neat. So this comes about because if you want to look at, let's say, x dot 1, which is equal to q dot, and then that would become, j would have to be different, so it would be omega 1, 2, and h2, and that would just give me h2, which is just this boy. dpi, yeah. It's neat. But no, that can be, that's just a very generic way of writing all of the Hamilton's equations down. Now, moving on into kind of the main meat and potatoes of this, I'm actually going off of the textbook called Chaos Book. It's written by Predrag. I can't actually pronounce his last name, so that's okay. And the full PDF with the full derivation will be listed in the description, hopefully. So I'll mostly skip through that, but effectively, let's see what happens is, let's see, that we want to apply a transformation to the system, some Hamiltonian flow of, we want to apply a transformation of H, which is just HI, XI, as I said previously. Now what we want is something that retains the whole Hamiltonian equation form, so we want a transformation that leaves this form invariant. It's called a canonical transformation, and this is just very useful throughout a lot of physics, actually. It seems to be. So from here, we want to define a new function based off of the old function of the Hamilton. So we just say HHX, where the x is just equal to the x up there, and the h is the transform, and well, little h is the transform, and big H is the original Hamiltonian. Now, we want to put constraints on H to just show us like a general idea of what this H needs to be. And to do this, we will employ the chain rule, which brings us to Kj, again using the notation here, equals to H L S L J. Now, here S I J is equal to D H I D X J. Yeah. And it's pretty great. And then in this case, the comma notation is equal to the partial derivative with respect to y, which is the new coordinate system. Alright, so we have our nice little equation there. From here, let's see. From here we can write that dl h is equal to negative mega lm j dot m, or not j, y dot m, and this is just via the chain rule, and just trying to get this is just a rewritten form of this equation, which is just the new way to write this notation, and then taking advantage of the fact that the inverse of omega is equal to negative omega, because omega squared is equal to negative unit matrix. So all we have to do is just multiply both sides. We'll take the derivative, both sides, multiply by the antisymmetric matrix, and we have this form. Alright, so from there, so we're just using this information. Since we had to multiply both sides by, we'll take the derivative on both sides and multiply both sides by omega, our original equation becomes ij delta jk equals negative ij sj l omega lm sm and xn dot. This is, again, from back here, we just took the derivative of both sides to get that, and then multiplied it all the way through, and just separated out the y dot m derivative. I'll turn on the light there. Ooh, that is... There we go. Alright. So, what we want is we want the right-hand side to simplify down to xi. So that way it will retain the form derivative of k multiplied by the antisymmetric matrix given. And the only way this can happen is if a whole bunch of terms cancel out. So equals omega ij slj omega lm smn. If that all goes to the Dirac delta function of I and n, which is just 0 when I is not equal to n, and 1 when n equals I. So, yeah. Or we can rewrite this in forms of like full derivatives and the full matrix instead of just indices as omega dh t omega dh equals unit matrix. Again, this is just Dirac delta function on the diagonal, reflecting that the same indices have to be ones. The transpose is from the fact that you have to resolve indices, so this has to be equal to the transpose of dh, full derivative of the transformation, and yeah. Then we'll take advantage of the fact that this can be used as a transpose to, inverse to get dh omega dh equals omega. Alright, so now this is the condition that symplectic matrices, or members of the symplectic group, fulfill, is G transpose omega G equals omega, where omega is antisymmetric and omega transpose is equal to negative omega, and omega squared is equal to negative I, which in this case the omega that we are using, fulfills both of these. So in this case, G is equal to dH, which must be symplectic. Alright. So basically, all summed up, if we apply a nonlinear transformation to a Hamiltonian flow, and we want the form of that equation to be invariant through this transformation, invariant to this transformation, we need the full derivative of h to be symplectic, or satisfying that, where omega is equal to negative I 0, 0. Alright. Neato.